Hello everyone, and welcome to my presentation on how response time models can separate single and dual process accounts of memory-based decisions. When making real-world decisions, such as where do we want to have dinner or what are we gonna buy in the supermarket, we use information from memory. These can be factual knowledge or autobiographical events from episodic memory. When having retrieved this information, we can use it to inform a decision process, leading to an ultimate choice. However, memory-based decisions are prone to different sort of biases, which violate classical economic theory. One sort of these biases is what we call the memory bias. This bias refers to the phenomenon that people do not only choose options because they are good, but also because they have good memory for them. For instance, I may choose to eat at a relatively bad restaurant, such as McDonald's, instead of an alternative one, just because I don't know the other one as well. Although chances are that the alternative is better, people tend to prefer the unattractive option here. Psychologically, you may think of this as an "at least I know what I get" attitude. Research showed that this memory bias is partly due to subjective beliefs about memory strength and shows characteristics of decisions under uncertainty. In this talk, I want to find out what are the cognitive processes which give rise to the memory bias. To do this, I will first familiarize you with the Remember and Decide task where we found this bias. Next, I will propose a single process and a dual process account in the diffusion model framework to explain the phenomenon. I will show how both accounts can be tested regarding their qualitative predictions, and lastly, how we obtained parametric fits in a hierarchical Bayesian framework and performed quantitative model comparison techniques to compare them. Our group identified this bias in an experiment where participants first gave subjective ratings on their preference about many snacks from different snack categories. Then they faced the Remember and Decide task, which consisted of the 4 periods encoding, distraction, decision, and recall in that order. During encoding, participants saw 6 empty squares on the screen. One after another, each location was highlighted, and a snack image appeared in the respective square. Participants had to memorize which snack belonged to which location on the screen. Here, the lower left square is associated with a chocolate bar. After a distraction task, participants entered the crucial decision period. Here, the 6 squares were presented again. In each trial, 2 squares were highlighted. Participants had to choose one of the 2 snacks, which were, so to speak, hidden behind these white squares. Since the snack identity was not visually accessible, they had to retrieve it from memory in order to make an informed choice. During recall, the snack location associations were probed to check whether people could remember the snack item associations. Now, in some trials, people remembered both options and had full knowledge about the hidden snacks. In other trials, they forgot both options and exhibited random choice behavior. However, when people remembered one option and forgot the other option, they tended to choose the remembered option even if its subjective value was comparatively low. This is described in this empirical choice curve here, where the fraction of choosing the remembered option is depicted on the y-axis and the value of the remembered option is on the x-axis. These are z-transformed values, so that the average snack value is at 0. You can see that people are indifferent between both options when the value of the remembered snack is below average. Participants acted as if they would compare the value of the remembered option with a reference value, which seemed to be biased to prefer the remembered option. So they would be more likely to discard options below this reference value and choose options which have a higher subjective value. We tackled this problem with a diffusion decision model. In its original form, the DDM maps choices and response times to 4 latent variables. First, the boundary separation indicates the relative amount of evidence required to terminate the accumulation process. Second, the starting point bias determines the amount of relative evidence at the beginning of the accumulation process. Third, the non-decision time includes processes that are not part of the accumulation process, such as visual encoding time or motor execution time. And finally, the drift rate determines the speed of evidence accumulation. In value-based decision-making, the drift rate is often proportional to the difference in subjective value between two options. But how can an agent assess a value difference if she only knows the value of one option but has forgotten the value of the other option? Our group proposed that, in such a scenario, people would compare the value of the remembered option with a reference value gamma. This comparison determines the drift rate. If gamma is negative, the DDM would predict a choice curve and a response time curve to look similar to this here. Accordingly, we would expect that people are indifferent between remembered and forgotten option when the value of the remembered option VREM equals a negative value of gamma. On the other hand, if drift rate is 0, the DDM expects a long-lasting accumulation process. Therefore, the expected response times would be maximal when VREM equals gamma. Note that these qualitative predictions only hold if one assumes no starting point bias and no variability in the DDM parameters. An alternative explanation comes from the framework of dual process theories, which is very popular in psychology and behavioral economics. These theories usually imply that decisions come from two types of processes, one intuitive, fast type 1 process and a more elaborated but slow type 2 process. These processes were suggested to play a critical role, especially in memory-based decision-making. Despite their popularity, dual process approaches have been criticized substantially by various researchers. Most criticism aimed at weaknesses of internal coherence of these theories, as well as a lack of empirical support. Apart from that, an additional hurdle to test these theories is that they are rarely formalized. This impedes quantitative model comparison and critical empirical testing. Recently, however, there have been models suggested which incorporate the idea of dual processes in the sequential sampling framework. Especially interesting for us is the dual process diffusion model by Carlos Allos Ferrer, which can be applied to value-based decision-making in a straightforward way. This model suggests that people vary between two types of choice strategies across trials. In some trials, people use a utility maximizing process which captures the computational normative aspects of decision-making. In other trials, a heuristic process favors intuitive affective attributes of a choice option with a relatively high drift rate, leading to fast and consistent responses. The model assumes that both run at the same time and independently from one another, and that in every given trial, the central executive selects one process to give rise to the choices and response times. This is modeled as a biased coin flip depending on the parameter delta. To explain the memory bias, we propose that the utility maximizing process reflects a comparison of VREM and the average snack value to select a choice option of high subjective utility. The expected choice curve of such a process would have an indifference point where VREM equals the average snack value. The response time curve would have its maximum at the average snack value. The heuristic process, on the other hand, may resemble a recognition heuristic where people make fast choices for a snack because it can be recalled correctly, independent of its actual subjective value. You can see the course of this process as red dotted line here. As you see, the process more likely chooses the remembered option, but choices and response times are independent of its value. If you now assume that people sometimes use the heuristic process and other times the utility process, what you would observe on the participant level would look like a weighted average of these curves. As you can see, this model would produce a choice curve which would look very similar to the choice curve that we see in empirical observations. It further makes predictions about response times. As you can see, both the single process and the dual process model make similar predictions with respect to choices, but differ with respect to response times. Therefore, response times are especially informative for testing if a single process or a dual process model accounts for the data. We tested these predictions with empirical data of 90 participants collected in a previously published study. The response times are shown here in this graph. To test the model predictions, we fitted a measurement model which described a quadratic function with an intercept beta 0, a slope beta 1, and the bias term beta 2. Beta 2 can shift the curve to the left or to the right. Importantly, if this beta 2 term is positive, the response time curve is shifted to the left, in line with the predictions of the single process model. If it is 0, the curve does not shift, and this would be evidence for the dual process model. We fitted this as a hierarchical Bayesian regression model where participant-specific parameters came from group-level normal distributions. The mu parameter of beta 2 was estimated with a posterior mean of 0.62. The highest density intervals excluded 0. This analysis demonstrates that the single process account is to be preferred here. Alongside with these qualitative predictions, we wanted to see if there's also quantitative support for the SPDM. I am keeping this short in the interest of time. If you're interested in the details, please consult the preprint of the study. We modeled the data as coming from a first-passage Wiener process. Boundary separation, starting point bias, and non-decision time were free parameters which could vary from participant to participant. The drift rate was determined for every trial individually, reflecting the comparison of the subjective value of an option in that trial and the participant-specific reference value gamma. We implemented the DPDM as a mixture model, assuming that a proportion of trials delta would come from a Wiener process with the utility drift rate and 1 minus delta would come from a Wiener process with the heuristic drift rate. Both processes differed only with respect to the drift rate. The drift rate of the utility process was analogous to the drift rate in the SPDM, but with the average snack value as a reference value. The drift rate of the heuristic process was a free parameter which was determined to favor the remembered option. We estimated these models with STAN using 4 chains of 10,000 samples each, getting good convergence with all R hats smaller or equal than 1.01. Having these models estimated, we computed posterior predictors by generating artificial data sets from our estimated parameter distributions. We checked how well these datasets match the actually observed data. What you can see here is that both models do exhibit an indifference point at a negative value of VREM, thus capturing the memory bias on choice. Looking at the response time data, we observe that the single process model covers the real data quite well, while the dual process model seems to be systematically misfitting the data. More specifically, on the left, it underestimates the response times to some degree, on the right it overestimates them. Finally, we wanted to perform model comparison while penalizing for model complexity. Using our posterior samples, we calculated a widely applicable information criterion for both models. Here as well, the single process model performs better since we observe a lower WASC. To sum up, in this study we compared a single with a dual process account of memory-based decisions. The single process account assumes that people compare subjective values with a reference value, which is biased, so they are more likely to choose options with better memory. In contrast, the dual process account assumes that people in some instances behave sort of rational, while relying on a heuristic in other trials. We found that both accounts can explain the choice behavior we see in the remember and decide task. However, when considering response times, we observe consistent support for the single process model. We have estimated the parameters of both models in a hierarchical Bayesian framework. We provide parameter and model recovery analysis showing that both models are identifiable. All data and code will be available online on OSF once the study is published. For now, you can find a preprint on PsycArXiv. We think that our approach provides a principled way of testing dual process theories. We hope that such an approach can move the debate forward by showing how dual process models can be tested, adhering to empirical findings and methodological rigor. With this, I would like to thank my collaborators, Laura Fontanesi, Michael Spector, and Sebastian Glut, who have contributed to this work. And last but not least, I would like to thank you for your attention and hope to see you in the Q&A session. Bye-bye.